Good day, friends. Today we're going to discuss something called circular aperture. This is the continuation of the previous topic, which is wave optics, single slit experiment, double slit experiment, also diffraction grating. And if you remember, we have mentioned circular apertures as well in the last video. But the reason why we dedicated one video for first three of them and another video for circular apertures, the thing is, we said that those three have pretty much the same formula, pretty much the same concept. However, when it comes to circular aperture, it's a little bit different. It is not totally something new, but it has a little bit different idea. Okay, good. So let's move to the topic itself. Okay, so if you remember last time, we have discussed already what is single slit experiment, double slit experiment, and so on. So it's pretty much the same concept, almost. Yeah, we have such kind of, for example, the plastic plate, let's say, but this is not a slit. As usual, it's a circular slit. In fact, it looks like this. Okay, so if we had something to show you from the side, it would be something like this. As you can see, we have this kind of plate. Of this part is maybe some plastic, maybe something else. It doesn't matter. But the main thing, there must be some hole, which is pretty much small. In fact, okay, it's something very small. Okay. So as you can see, if we pass some beam of light with some wavelengths, then it goes to the center, then it creates such kind of pattern, yeah, as you can see. So if you look at this one, you can see several factors, for example, the diameter of the slit, yeah, circular slit, or aperture, better to call it aperture, yeah. Also some width of the central maximum, yeah, you can see here that in the center it has some high intensity, which is this one, and then it has some small and smaller maximums, which are this one, and this one, and this one, and so on and so on and so on. Okay, so good. And also we have here the light intensity, which is this graph, yeah. P, it's pretty much the same thing as M in the double slit experiment. If you remember, we had something like d sine theta equals m lambda, and P plays pretty much the same role as M in circular apertures, yeah. Okay. Good. Also, one more thing to note, when we deal with circular apertures, it has only one hole, yeah, it is not many holes. That's why, if you remember last time, we have mentioned that in single slits, when we talk about M's, yeah, for example, this M equals 1, it is for dark fringes, not for bright fringes. If it was diffraction grating or Young's double slit, then M, if it was a full number, like 1, 2, 3, and so on, then it would be a bright fringe. If it was 1.5, 2.5, and so on, and so on, and so on, then it would be dark fringe, but not for single slit and not for circular aperture. For single slit, if M is a full number like 1, 2, 3, then it's a dark fringe. It's a dark fringe. For circular aperture, it's pretty much the same. As you can see here, P equals 1, it's a dark fringe. You can see here very low intensity, even we can say there is no any intensity, it's just dark. You can see here it's a dark part, yeah. Also P2, it's a no intensity, P3 no intensity, and so on and so on and so on. Okay, good. If you understand it, it's pretty good start. Okay, so let's move to this one, yeah. If we just draw pretty much the same concept here in 3D form, then it would be something like this. For example, let's imagine some kind of plastic which has some very small hole. Then we would have this kind of pattern, as you can see, yeah. It's pretty much obvious because we have already shown it, this one, yeah. This thing is called airy disk, and this is important because sometimes if we are given in problems this kind of word, then you should know what it is, okay? So we pass here some beam of light, for example, for convenience, let's say this is red one, yeah, this is the highest wavelengths. Then we have some diameter of this aperture, and then we have these angles which are theta 1, 2, 3, and so on. And as you can see here, I've specially noted the first line to the center as white one because the central one, we know it's a maximum. However, all the next ones are gray. In fact, it was meant to be black, but as you can see, the screen is black. That's why you wouldn't be able to see it. But the point is, these lines go and indicate the dark fringes. As you can see, the dark fringe, yeah, these parts are all dark fringes. And these angles look at dark fringes, okay? They look at dark fringes, not bright fringes, okay? So we have this kind of formulas, in fact, just one formula, but in different kind of form. And it might be a little bit strange to you, yeah? Look at this one. As I have said, when we deal with lambda, or with theta, I'm sorry, when we deal with certain theta, we work with dark fringes. And here we have the first minima, yeah, the first angle, which is exactly this one, yeah? And then we have the second minima, okay, it was meant to be theta 2, it was meant to be theta 3, there is a mistake. So this one is meant to be this one, and this one is meant to be this one, yeah? Okay, good. Also, we can find some maximas, 1.63, this kind of. Again, it must be 1, this must be 2, this must be 3. A little bit mistake, okay. Only thing that is a little bit not clear to you, maybe, yeah, this thing. You pretty much understand what is going on here, I hope, because if you remember, we had something like this in last time, d sine theta equals m lambda, right? And if we wanted to find theta, then it would be sine theta equals m lambda divided by d. D was a distance between two, just the distance of the slit. Or for single slit, it would be the difference between two edges of the same slit, right? Okay, good. And if it was a small angle approximation, then it would be sine theta equals theta, yeah, sine theta equals theta itself. Then this thing would be m lambda divided by d. Good? Yeah. It's pretty much the same thing, yeah. So theta comes from this one. Lambda, as you can see, it's here. D is this one, this D, the large diameter, yeah. But what about this M, which was here, this M? This is 1.22, yeah. Here, for the second minima, it is 2.23. For the third one, 3.24, and so on and so on. A little bit strange numbers, in fact, and you might think, where did I get those from? But let's talk about them right now, yep. Okay, let's move to this one. Let's give some definitions to each one of the factors that we are going to apply in our formulas. So, factor number one, lambda, which is wavelength, you know it pretty good, yeah. Diameter, okay. And here we have the radius of the circular aperture. However, let's define it as A, not R. Why? Because we already have R here. Also, we have central maximum, and its radius is defined as R, yeah. Okay. The distance between this circular aperture and the screen that we are projecting the image on, we call it L as usual. And the theta, as I have said, mostly we will concentrate on dark fringes, but let's give the meaning to the theta, the minimum value. It would be this top point of this red central maximum, okay? Okay, and this angle would be theta. Good. Okay, right now we know that A is just a half of diameter. Okay, we already know that. Again, we can apply here just the sine, the meaning of sine theta. Yeah, sine is opposite divided by adjacent. Our opposite is this R, our adjacent is this large L. However, it's a very small angle, as you can see here. It's a very good image because it shows how small the angle is. That's why we can use small angle approximation. Sine theta would be equal to theta. So that's how our theta will have this kind of meaning. Okay, good. What does it give us? It gives us the angular size, something called angular size. We're going to discuss about it a little bit later. Okay, good. Let's move to this thing. A little bit strange thing. Maybe you haven't heard about it. This thing is called Bessel function. Okay, basically, what is Bessel function? Bessel function shows us something like this. For example, if you have some stone and you drop it to the water, to the very smooth water, then definitely at one point it would splash. And when it splashes, it would have something like this kind of pattern. Yeah. So basically, pretty much the same thing as our graph, like here, right? If we have, for example, if you rotate this thing, for example, if you're trying to rotate this thing, if you take it and then you rotate it, so it was like this one, this our image would be something like this one, and so on. It appears that, for example, if you drop the stone to the water, at one point it will splash, and then it would give us this kind of pattern. And Bessel function shows us what that splash would look like. It would be something like this kind of pattern, and it would have this kind of formula, but we don't need its origin, in fact, and we are not going to use it, in fact, but we need to know that Bessel function of order 1, this one is important. So also we have here k, some value of k, which wave number, yeah, you definitely know this from your oscillations and waves topic, something like this, x equals amplitude cosine, this would be kx minus omega t. Maybe you remember this thing, and k comes from there, it comes from the wave, okay? And it has pretty much logical value as 2 pi divided by lambda. Also we have here sine theta equals r divided by L, and we had it from here, yeah, we had it from here. Okay, good. Why do we need those things? Because you can see here, we have here j, which is right here, we have here k, which is right here in the formula, we have sine theta, which is this one, yeah, okay, good. Okay, yep. Also we have here A, which is our, this one, yep, diameter divided by 2. Good. Right now, you can see here the Bessel functions graph, which looks like this, and it has pretty much a constant numbers like this one, 3.832, 7.016, and so on and so on and so on. We're not interested in those numbers, but we are interested in understanding them. Okay, these points are the minimums, yeah? These points are the minimums where if we have a splash of water, for example, like this again, like this, these numbers, these red numbers, they indicate these minimums, like this is the first order, this is the second order, then we have maybe some, this kind of, this is a third order, maybe something like this, okay? These are minimums, yeah? This is not minimum because it's below. This is not minimum because it's below. This is maximum. This is minimum, okay? Okay, I hope you understand it. Let's work with minimums because, as we have said, in circular apertures, we mostly concentrate on minimums. Okay, if we apply the first order, this one, yeah, then we can take this thing inside, yeah, because that's apparently, for example, you might think, why don't we just cancel those two out? Because these two are function. this is a function, 2j function of ka sine theta. It is not a multiplication of something to cancel this out. You cannot cancel it, okay? So if we take that value, ka sine theta, okay, let me write it here. Yeah, first minimum. Let's work with this one. Okay, what is it? Ka sine theta will be equal to 3 point, what it is? 832. Okay, right now let's open these factors by their meanings. For example, k is here, 2 pi divided by lambda. This is 2 pi divided by lambda. A is our half of the diameter. Sine theta is here. It is r divided by L. This is r divided by L. Then it's this thing would be 3.832. Okay. Let's cancel these twos out. Then, as you can see here, we would have what kind of answer? P dr divided by lambda L equals 3.832. Okay. If I move everything to the another side, then you see something like this. The formula for radius would be this 3.832 divided by pi. We can open pi. Yeah. Also, what we have here lambda L divided by what? This d. Okay, d. And if we open this p, then we would have something like this. R equals this 3.832 divided by pi is a 3.14 multiplied lambda L divided by d. Okay, doesn't it remind you of something? Okay, if you just imagine yourself how you can calculate it, then you'd have something like this. R equals, this is about 1.22 lambda L divided by d. Okay, something very close to our formula, as you can see. And this is for R. Yeah, we just use it for our radius formula. Let me note it with green maybe. But if I bring back that L, yeah, then it would be R divided by L, 1 divided by 22, lambda divided by d. And R divided by L, you remember this thing? It would be sine theta, or our just theta, yeah, equals 1.22 lambda divided by d. And that's how we get our formula. Yeah, so basically it originates from Bessel function. We don't need to know the origin of Bessel function. Yes, it is good if you know. It is good if you know, but you don't have to stick to it. Yeah, because the main thing you should know the physical part of it, not the mathematical. Okay. If you ask me, yeah, why did I open up that sine theta from the very beginning? If I again at the very end I had that sine theta, so I didn't need to open sine theta, because at the end it would be again sine theta. Why did I open this up to complicate it? No, instead I just wanted to show you the formula of the radius of the airy disk. Yeah, and I hope you understand right now. How we have that formula 1.22, and as you can see here we have other numbers 7.16, 10.173, and if we continue to put those numbers in, instead of here, then you would have these numbers 2.23, 3.24, and so on and so on and so on. So that's how we have these formulas. Okay, good. Right now, let's move to the practical part. A little bit practical, not the problem solving, but still something to understand. Okay, there is something called angular size. Okay, what does angular size mean? For example, let's imagine these two boxes, this one and this one. Okay, do you think that those two boxes are different size? Maybe you think so, but in fact it's not. Basically, those two things have the same volume, as you can see here. They have the same height, they have the same width, and also they are equal from all sides, yeah? They have the same area, and so on and so on and so on. Their sizes, their actual physical sizes are the same, the very same box. In fact, it is this one is this one. It's not separate boxes. Those two are the same box, in fact. Only thing that happened, this human being just moved a little bit closer. And as you can see here, as human being goes to the box, then this thing gets bigger. But in fact, this thing does not get bigger. As you can see here, I have written here, object did not physically get larger. It does not get larger. It does not enlarge. Only its angular size. As you can see, this angle, yeah, angular size 1 and angular size 2. Only that thing differs in two situations, not the physical size of the box, okay? Okay, good. What about this one? Okay, right now let's try to connect our knowledge of circular aperture and this angular size knowledge, okay? For example, we can have some blind spots. You probably know that thing, what the blind spot is. Yeah, for example, it's the places that you cannot see. For example, if somebody touches your back and then you have to turn over, but if that human being or your friend keeps running on your back all the time, then you cannot see him. That is what the blind spot is, right? For example, here we have another friend of this person, and then he touches his back, and this person turns over, this person runs away to his back as well, and that's why this main person will not see his friends all the time, because his friend keeps running to his back, okay? That's what is a blind spot, yeah? But what if I say that your blind spot does not have to be exactly on your back? In front, you can also have very, very, very small blind spots, and let's talk about them. So I call this thing, well, generally it is called angle of resolution. There are some angles that smaller than which we cannot resolve two things. Yeah. For example, let's say we have this kind of situation. At very far distance, in very far distance, we have some car which is moving at night, for example. At very large distance, you see this thing as this one. Yeah. It seems to you that you see just one light. Maybe it's even like this. It's just one big light coming to you. At one point, you start to see that that one circle starts to become two. It starts to split away. At certain part, you see this kind of thing. At certain part, when it gets very close, you can see both of those lights together. Separately. I'm sorry. At the very beginning, you see it together. At the very end, they separate from each other. Yeah. Why? Because your angle of resolution, it is drawn like very large theta, but in fact, it is something very small. It is maybe something like this, and the smaller than this angle, you cannot resolve. For example, if you have two very small boxes here, then you wouldn't be able to resolve them and you would see them as one box because your angle of resolution does not allow you to see and distinguish those two boxes. The very same thing happens here. If your angle of resolution is bigger than angular size of the object, then you see everything inside of that angle of resolution as one thing. You cannot distinguish it, okay? And I hope that you understand it a little bit later, but the main thing, limit of resolution, the angular size of the object has to be large, at least equal to the angle of resolution. For example, when this car gets closer, it does not get bigger. Instead, its lights get like this, and you can see that its angular size gets bigger than your the resolution angle, okay? That's why you can resolve that thing. Okay, good. And maybe you ask me what is the connection and why do we need at all a human being? What does it have to do with circular aperture? Because our main topic is this one, circular aperture. Why do we need a human being? But in fact, your eyes are in fact a very good example of circular aperture. Yeah, because in fact, what you have here, your pupil, dark point in your eye, it is not something. In fact, this is just the empty space in your eye. Yeah, that's why we can accept it as a whole, and it is circular, it is small, and that's why we can consider it as circular aperture. Yeah. Okay. Good. And you might say that our pupil is not that small, but the thing is, the object that we are trying to see is too big. Our image, we see the entire world, we see mountains, we see the sky, and the object itself is so large, and compared to that, our pupil is very small. That's why we can consider it as circular aperture. Okay. The next question is like this: Can you see a human hair laying on the ground? Well, to see it, it's two parts, size, better to say it, like this. Its angular size must at least be equal to our angle of resolution, so we can resolve it. But if its angular size is smaller than our angle of resolution, then of course we cannot distinguish it with the screen that it is on. Okay. So angle subtend from both sides of the hair. Subtend, we mean that of these two sides. And that angular size, this has to be smaller than, if it is smaller than our angle of resolution, then we cannot see the object. But if it is larger, if its size is larger than our angle of resolution, then yes, we can see it. Why not? Okay. Right now, let's talk about something called Rayleigh criterion. Okay, Rayleigh criterion. What is it? So basically, we have such kind of thing. This formula, we know this formula, and basically this is Rayleigh criterion. But let me try to explain it in simple terms. For example, you have this kind of image that you see in your daily life, and at from each point, you receive some information. This point, and all the points that are between them. You receive many rays of light that are approaching and entering your eye. Yeah? But we need to remember that we are still in wave optics, not ray optics. That's why it has something to do with waves, not the rays. Okay. That's why let's work with definitions so you understand it better. The rule number 1: each point emitting or reflecting light creates circular airy disk. Okay. Something might emit light. Yeah. For example, like the light bulb. Something can reflect light. Yeah. It will not emit light. For example, I'm sorry. Yeah. So for example, this tree that we have here. Yeah. This is a tree, and this tree does not emit any light. No, it reflects light that comes from the sun, and then it goes to our eyes and so on. But it does not matter. Each of those things create this kind of pattern. Each point creates a circular aperture. Yeah. This kind of pattern, airy disk. Then the second rule: image is the result of the summation of all these airy patterns. So we have many these kind of patterns that are entering our eyes, and all of their combination gives us the image that we see in our daily life. Okay, and the last thing, when two very close points create airy disk patterns that don't interfere but overlap on each other, they create higher intensity. Airy disk of 2 points get indistinguishable. What does it mean? Okay, let's get back to our image. Yeah. So, for example, can I distinguish this tree from this house? Well, yes, I can. However, can I distinguish this point of the tree and this point of the tree if I'm too far? If I'm too close, yes, of course, it's pretty much easy to distinguish that point. But if I'm so far, is it easy for me to distinguish these 2 points? Well, maybe not. If I'm too far, definitely not. Why? Because each of those 2 points create airy pattern, right? And at a certain point, when they collide to each other, so close, at a certain point, those two become just one airy disk, like this, yeah? And you start to not distinguish those airy disks with each other. It becomes harder to distinguish those two. It becomes harder to resolve those two. That's why instead of interfering with each other, yeah? Because interference is the most important thing to us. The image that we have on the screens, yeah, for example, like this one, they are created due to interference. Diffraction is just a fact. Diffraction just a bending of light after it hits some obstacle. Yeah, light comes like this, and then it hits this obstacle, and then it creates some diffraction. It's just a fact. It does not give us something, but interference gives us information. It gives us where the constructive diffractions they create our bright spots, where it creates dark spots, and due to interference we can see everything very well. Yep, good. However, when two that kind of airy patterns that come to our eyes from different points, and those 2 points are too close to each other, then the problem is that they do not interfere with each other because they are too close, and instead they overlap on each other, like this one, like this. They overlap, and they create higher intensity. They create intensity instead of some new image, okay? Airy disks of 2 points become indistinguishable, so I hope that you understand what it is, yeah? Okay, if you understand, it's good. So we have many rays that are approaching your eyes, and those waves, they create interference. Definitely due to that interference you receive some information about the outer world. However, when 2 points, for example this point and this point, are too close, then you cannot distinguish it. Instead they create higher intensity but not something different. Okay, good. Let's right now solve some problems. Okay, we have a normal human being's eye, which has a diameter of between 2 and 9 millimeters. Let's take 4 as an average. Yep, let's take 4 as an average. Let's take the wavelengths of light. Yep, let's take. We have many colors, of course. The spectrum of the visible light starts from 380 nanometers to 760 nanometers. This is the violet color, this is the red color, and yeah. But in average, let's take this lambda as 500 nanometers to not complicate it, just the theoretical problem solving. And let's see if we can distinguish something, yeah. What would be the distance between two things, yeah, between 2 points that we can distinguish, yeah, from 25 centimeters, from 100 meters, and from 20 kilometers, yeah. Okay, and well, the factors, yeah, there might be some factors which also can cause us, but we do not take those into account. It's those are air quality, vision, color, contrast, lighting, and so on, yeah. Okay, so let's imagine our situation like this. You have some mountain like standing like this, and let's say that you have here 2 friends. You have here friend 1, friend 2. And for example, if you are very close, in fact, you can distinguish them. You can definitely see both of them. But as you get far, those two will seem to you like these 2 tops of the mountains. They get closer. And at a certain point, this angle of resolution that you can distinguish becomes so small that you cannot even resolve those 2. That's why they become something one. And then both of your friends, they will merge into each other. Yeah. Okay. And that distance from mountain to you is L. Okay. So what we should do first is apply our this formula, which is theta equals 1.22 lambda divided by d. Okay. So if we apply these numbers, it would be 1.22 multiplied lambda is 500 nanometers, which is 10 to the power of minus 9, and here we have d, which is 4 millimeters. This is 4 multiplied 10 to the power of minus 3. Okay, let me calculate it. 1.525 10 to the power of minus 4 radians. Okay. So what angle is this? Is it our angle of is it our angular size, or is it our angle of resolution? In fact, as I have written here, those two must match up to find the minimum distance that we can resolve. That's why our minimum distance would be what? As we have said, so our angular size have to be more, or at least minimum be equal to our angle of resolution. That's why we take that equal sign, the minimum angle that we can resolve. Okay. Good. The second formula, okay, here let's try to write it here. So r would be distance, because if you remember, r is our distance between those two things. Yeah. So our theta would be what? Our theta is this thing, 1.25, 1.525, 10 to the power of minus 4. Why? Because if we want to find r, it must be theta multiplied L, right? Okay. This thing would be, instead of L, we put what? For A option, we put 20 kilometers. Kilometers is 10 to the power of 3. And that's how we get our answer, which is 3.05 meters. Okay, what does it mean? From 20 kilometers, if we look at some mountain, and the distance between those two would be 3 meters, for example, then those two would be almost indistinguishable to us. Yeah. Why almost? Because as we have said, there are many factors. But if we have two friends of ours standing on the top of those two mountains, and the distance between them is 3 meters, then it would look to us that we are staring only on one of our friends, because those two, the light which approaches from both of them, will overlap on each other. That's how we cannot distinguish it, right? Good. And let's use the very same thing for r. That would be again 1.25, 10 to the power of minus 4. L would be what? L would be right now would be 100 meters. So this thing would be 1.5, 10 to the power of minus 3. Or it would be something about 1.5. Okay, not minus 3, I'm sorry, it's minus 2. Minus 2. This would be then centimeters. Okay, 1.2 centimeters. So if we look at something from 100 meters, in the perfect conditions, we cannot resolve between 2 points which are 1.5 centimeters apart. Those 2 points would look to us as 1 point, okay? The next thing for C, let's use the very same thing. Our theta, which is 1.5, 25, 10 to the power of minus 4, and multiply 25 centimeters, which is 10 to the power of minus 2, then we would have some answer which would be about 0.038 millimeters. Okay, 0.038 millimeters. What does it mean? It means that if we have something very small like this, and its width is just 0.1 millimeter, then, if we are looking at this thing from 25 centimeters, we would still manage to resolve 1/3 of this object. So if this small, I don't know, maybe human hair, maybe something, if this thing was even smaller, 3 times smaller, we would still be able to manage to see this thing. Because if you decrease it by 3, it would be almost this value, and we would barely able to resolve those 2 edges of the hair. Yeah. Right now, let's work with the hair itself. Okay. So we have this kind of situation. Would we be able to see a human hair which stands in 1.5 meters from us? Okay. To do that, we need to take these values, which are the diameter of the hair. As you can see, we need to take the distance between 2 edges, which is the basically diameter, and the diameter over here comes from 0.17 millimeters to 0.180 millimeters. Okay. And would we be able to resolve them? To solve this problem, what we are going to do, we need to find just this the minimum diameter of anything that we want to be able to resolve. And if this number would be between these values, these 2 values, then definitely we can see it. And if it is smaller, then of course we cannot. Okay. So let's do something like this. We have this formula, which is sine theta, or let me write it as theta divided by r divided by L, and we need to find that r, which is L multiplied theta. Okay, theta. Our minimum theta of resolution would be 1.22 multiplied lambda. Let's take it as this one, the very same values, 500 nanometers, and diameter also for the eye, 4 millimeters. Then if we apply those numbers again, then we would have the very same value. This is 4 millimeters, which is like this, and then we would have the very same value, which is 1.525 multiplied 10 to the power of minus 4. This is radian, this is not angle, okay? And if it is that value, then that r, this is not radius, but instead the size of the object, angle, and our L is 1.5 meters, and this thing is 1.525 multiplied 10 to the power of minus 4, and then we would have some value which is like 0.029 millimeters. Okay, let's see if that value is between them, and as you can see, it is. It is definitely larger than this 0.029 17 millimeters, and it is definitely smaller than this, but it's still in that range. It's still in that range. That's why this value is enough. This is the smallest distance between 2 points that we are able to resolve. Smaller than this, we cannot resolve. But if our object was this value, yeah, if our hair was this kind of value, 0.017, then its angular size is smaller than our angle of resolution. Then, then we cannot. Oh, I'm sorry, not theta. Yeah, it's r and it's r. It's the smallest r, and this is r for resolution. Yeah, and if it was this kind of 0.017 millimeters, then we would not be able to resolve it. But of course, the hair can be larger than our value, which is, as you can see, 0.180 millimeters. Then of course we can resolve it. Good. And the last problem that we're going to solve for today would be this one. Okay, what is this? It is HST, which is Hubble Space Telescope. Okay, and it has pretty much large diameter in the camera, which is 2.4 meters. And the question is, what size crater can be detected? Okay, if it looks at the moon, what would be the smallest size that it would be able to detect, right? Okay, so is it given the value for this L for distance? Let me see. The value for L is given. However, I forgot to write it here. It is L equals 384 million meters. Okay, let's find the minimum angular size. That would be angle of resolution, which would be 1.22. Lambda would be, again, let's take it as average, 500 nanometers, 9. However, this thing would not be, again, that 4 millimeters. Instead, it is something larger, 2.4 meters. Here we write 2.4. And then our answer would be 254 multiplied 10 to the power of minus 7. And this is radian, right? This is radian. Okay, good. Let's try to find that the size of that thing. Our angle of angular size, of course, would be r divided by L, but these two things have to be equal, yeah, because that minimum value. So that size would be r theta multiplied L. L. Our theta is this value, 2.54 10 to the power of minus 7. L is that distance, 384 10 to the power of 6. Okay, these cancel out. This thing would be minus 1. And it would be the same thing as 2.54 multiplied 38.4. And it would be about 97 meters. Okay. Which means that the smallest thing that we can detect on the moon is about the size of the football field. Okay, the smallest thing that we can detect is about the size of the football field. But if this thing is smaller than the football field, if it is, I don't know, just 30 meters in size, yeah, then definitely our Hubble Space Telescope would not be able to resolve it. Yeah, it would not be able to distinguish it. The resolution would not be enough. Okay, so I hope that it was clear to you. If it was not, please write me privately, and I will try to do the best thing that I can. Okay, thanks for your attention. Goodbye.